Okay, so to begin with, we'll talk about Fewshot learning. And there was an original paper on this about 5 years ago now by Brendan Lake and colleagues that introduced this idea with this figure, and it's a good way of seeing it, where you have, up here you have some object that, let's say, you've never seen before, this segue. And now what the task is to take these other images down here and say which of those is the same object class as this segue up here. And it's a difficult thing, right? Because some of them look visually quite similar, but there's only one that we would say is actually a segue. Humans are very good at doing that. And the question is, the underlying question is, how can we adapt to new classes like this with very few labeled examples? And doing so is really an important step towards human-like AI. So for this talk, I want to focus on what's called Fewshot classification, and we'll define that here. So Fewshot classification is the task of adapting a classifier to a new set of classes at test time, given just a small number of labeled examples. So let's pull that apart so that emphasize what's novel here. So there's a lot of other terms in the literature, things like domain adaptation or multitask learning or meta learning. So here, like in this talk, I'm going to focus on Fewshot classification. And what's going to define that is that there's going to be a set of episodes, right? So every test is going to be an episode like what's shown over here on the right under test. So we have 5 examples of each of 5 novel classes that the system has never seen before. So these 5 rows, each one of those is a new class. And the task is to say, here's a query image. Which class of the 5 does that belong to? All right. And so this is an episode. And then the next test would be a new episode with a new set of 5 classes with just a few examples of each class. So it's called Fewshot because you just see a few examples of each class. All right. So that's the definition that was actually set up in that paper that I mentioned with the segue. And the key idea, again, is that we have totally novel classes unseen at test time. And we have some queries we have to identify as one of the small set of these test classes. There's also available some set of base classes that are different than the test classes for training up the system. All right, so that's these over here. So in this case, we train up on the English alphabet, a lot of characters in the English alphabet, and we get tested on a new alphabet with characters that haven't been seen before. Okay, so that's Fewshot classification. So in this paper, they also introduced a really nice data set for this task called Omniglot, and that's been called MNIST transpose, because in MNIST you have just a few characters, like 10 handwritten numbers, whereas in Omniglot, and many, many examples of those, in Omniglot we have many, many different characters from several different alphabets, and just a few, like 20 examples of each of those. Okay, so here, each column here is a different alphabet, like Sanskrit, Malay, Latin. We have different characters in that alphabet. And then a test, an episode would be of one shot, would be we have 20 different classes shown down here in this 4x5 grid. These are 20 different classes. And one example of each, so it's one shot. And then we have a query up here, and we have to say which of the 20 classes does this character belong to. Okay. So that's called the Omniglot data set. And in that paper, they also came up with a very nice way of solving this problem that used probabilistic programming. A nice alliterative title, probabilistic programming with parts. And they defined a set of primitives, some different kinds of strokes or that would be combined. Those would be the parts that could be select a few of them and decide how they're going to attach to each other. And through that, then there's some stochasticity in the actual appearance and how they relate to each other, so that you get different variants, in this case, 3 different variants of the same character. All right. And over here, you get 2 different variants of this character by selecting a different set of parts and combining them in particular ways, and another character over here. Okay. So this is the thing that actually got me very interested in this field. I like the approach and I like the problem. But one thing about it is that they had to predefine the set of parts that were involved, right? So this set of parts, these kind of primitives, were key to making this work. So one question is said, well, how could we do this with deep learning? Not having to define a probabilistic program where we predefine the primitives, but let's instead see how we can do with deep learning. So we did this using a form of a neural network called a Siamese network. And over here is a table of some results that we got. So humans get around 95% on the omniglot test, one of the omniglot test episodes, some of the omniglot test episodes. Their program, the probabilistic programming, was called hierarchical Bayesian program learning, and that got almost human level performance. And then our approach got the best version of our deep neural network, got 92%, almost approaching the probabilistic programming part. So this said that we can do comparably with deep learning, right? So that was a nice achievement. Since then, there's been a lot of work in this area, so I'd say that one of the central challenges in Fewshot learning is overfitting. So the idea is that you really have very little data in your episodes, in your tests, right? You have very few examples of these new classes. In the deep neural network, and that if you want to solve it with a deep neural network, it typically has many more parameters than is justified by the data. Now, in recent results, many theoretical results, they show that the deep neural networks sometimes can get away with having many more parameters than justified by the data. But it's still a question of you want to avoid overfitting to these few test examples, because here we have many fewer test examples than standard deep neural nets. Okay? So we can't revisit the base classes also because storage and time constraints and practical real-world problems. So the goal is to adapt quickly to new classes without forgetting about the base classes. Take some information from the base classes and use those to figure out how to do a good job with just a few examples of the test classes. So I'd say the work in the last few years that's gone on in this field, it's been a very busy field, and they can be divided roughly into 3 categories. One of them is called meta-learning, where the idea is that you want to learn a learning algorithm that's going to solve similar Fewshot tasks from the training set. So a couple papers in that area. One was a meta-learner that used an LSTM setup, and another one was MAML by Chelsea Finn and colleagues. Chelsea's talking tomorrow in this workshop. And so that's one very popular brand of, or strand of approach to this problem. Another one is metric learning. So metric learning, the idea is you're going to learn some embedding function so that Fewshot classification can work very well by just looking at distances of examples in the embedding space. The idea should be that if you get some new class, that the examples of that new class, even though you only have a few of them, they should be mapped to similar locations in this embedding space so that you can do a good job of classification on those. Okay? In our work that I talked about, the convolution, the deep network that did pretty well on the omniglot, that was a version of that. That was a Siamese network. There's other approaches that have been pursued in the literature here too. And the last kind of approach to this problem is data augmentation. So here the idea is that you want to generate more data by doing some transformations to those small labeled data set. And this is something that is common in deep learning overall. But what's novel about the Fewshot setting is that you want to try to figure out how to learn to transform the base classes such that you can apply similar transformation to the support, because again, you only have few examples from the support. Right? Overall, there's been fairly remarkable results over the past few years. It's not just with omniglot, it's also with more natural images like reduced version of the ImageNet called mini ImageNet has gotten some very nice results, very high accuracy with just a few examples of completely novel classes. Right? So that's really, I think, what's interesting about this. One of the interesting things about these new areas is some remarkable new results. In the last couple of years, though, some of the things that were key assumptions that we thought underlied some of these remarkable results have been called into question. So you can think of it like we take, often true in the field, you take 2 steps forward and then 1 step back. So the one example of this is that some work that we did with my group, something called prototypical networks, we said, well, we really want to have a very simple network to prevent overfitting, right? So we just had like a 4-layer convnet and showed that you could do very well with a 4-layer convnet in Fewshot classification. But then since then, some work has shown that, well, it's not exactly true. You don't need to have a very simple like 4-layer network. You can have a deep ResNet and do just as well. Another key assumption that people have made is that we're testing episodically, right? So that's one of the defining characteristics of this area. So we also should train episodically. So that's one of the kind of underlying tenets in machine learning, is that your training paradigm should match your testing paradigm to get good performance. And so this idea was promoted in this paper called Matching Nets, that let's train episodically and get very good results. More recently, some people have shown that you don't need to train episodically. You can do kind of standard batch pre-training and do just as well. So there's been several papers along these lines. One of them that says revisiting Fewshot classification. Another one shows that you can tune standard res nets, just do some fine tuning and do very well. And another one in the kind of meta learning formulation show, well, you don't really need the whole inner loop that Mammal has, where you do this bit of optimization on the test set. Instead, you do just as well without the inner loop. Okay. And the third assumption, or something that people have really promoted in the area, is that, well, we have to carefully craft how we're going to adapt at test time. Because, again, the overfitting issue, you want to have a very simple classifier on top of, let's say, a deep network. And that simple classifier will have parameters that can be adapted at test time, just based on those test episodes, and then thrown out for the next episode. You have to carefully craft how you're going to do that adaptation. So a version of this was promoted in, was proposed by a paper called Synapse, which was an adaptation of the conditional neural processes. And they did some very careful adaptation, including like some autoregressive component to the classifier on top of the network. And then just recently, there was another paper that would apply to that in some way that was called Simple. They had a method called Simple Synapse that didn't do very careful adaptation. They just said, well, all you need to do is per class have a separate covariance matrix and just adapt the parameters of that covariance matrix and get the same kind of state-of-the-art results that Synapse got. Right. So that's been a general trend here. We're calling these things into question, but some of these are really still questions. Like, for example, the idea that you could do just as well with a deep ResNet. Well, people have shown that some of those results depend on having larger images, for example, than the original images that were trained on. So I think there's still lots to be explored in this area. What I would suggest is that what we want to do is go beyond these current benchmarks. So one example of doing this is we should be looking at data sets that have different sorts of class structure. So in the original Omniglot splits by Brendan Lake and colleagues, they had different alphabets in each episode. So you saw new characters that were all from the same alphabet in each episode. So that kind of structure, that kind of interclass structure, is very important because it's generally a harder problem to tell apart examples of characters that are from the same alphabet. So that's the kind of structure that's important. We tried something similar. We said, well, in the ImageNet, when we're dealing with more natural images, we can also build structure into our data sets, into our episodes, by having different episodes explore different parts of the ImageNet hierarchy. And we can train on one part of the ImageNet hierarchy and test on other ones and ensure that we aren't going to see that the classes are very different. Right? So we're testing and training on distinct kinds of classes. And so far, I haven't seen any methods in this area that really take advantage of this kind of structure in the ImageNet classes or in the Omniglot classes, right? So the question is, when the training classes and test classes are quite different, the semantics of the classes might be very important. Another kind of thing that I think would be useful in pushing the forward relates to what Pushmeet was talking about and what a lot of people have worked on, which is, can we really test the robustness of these methods? We want to push beyond IID training and testing. We want to say, okay, what happens if we corrupt? We add input or label noise. I apologize for my dog barking. Input or label noise in the to the inputs, test the robustness of the system, and also do things like out of distribution detection. And another thing is to look at the uncertainty of these methods. What we want to explore is how well calibrated are these systems, and do other kinds of evaluations of uncertainty, as in this recent paper, Can You Trust Your Model's Uncertainty? Evaluating predictive uncertainty under data set shift. This is another way of testing beyond our current benchmarks and seeing really how well can we do on these kinds of few-shot classification problems. So I mentioned this idea, show you a picture of the domain shift example. So this is a recent paper that promoted something called metadata set, where the idea was that not only would you test on different parts of the classification hierarchy, but you could also train and test on very different data sets. So you could train on ImageNet and test on aircraft. So you have things like aircraft where you want to tell apart different kinds of aircraft, that kind of fine-grained classification. You can do fine-grained classification of different kinds of birds. And so the question is, if we learn about birds, how well can we do on novel, if we test on episodes that are drawn from novel classes of aircraft, right? So that metadata set is another way of really pushing on these methods and seeing what is important about what you get from the base classes that allows you to do a good job on the test classes, or not do a good job, as the case may be. Okay, so I'm going to focus now and switch to a particular approach that's focused on this idea of uncertainty and robustness. And I should say that now I'm going to talk about some current work, as yet unpublished, submitted, but about to appear on arXiv any day now. That's done with my student Jake Snell, and I should give him credit for, make sure he gets credit for all the good ideas that are presented here. So here's the aims that we want to do. Think of it as Bayesian few-shot classification. So the Bayesian approaches are a natural for few-shot classification. It's a good way we can want to combine the prior knowledge that we can get from the base classes and use those to our small bit of observations at test time. So introduce some notation, the standard few-shot classification setup. We're going to have a support set where we get pairs X and Y. X is the example, so we have n examples. That's each row in the matrix, and each of them is d-dimensional. And Y are the labels. So the labels, there's going to be C different classes, and they're going to be binary labels. They're going to be one hot label. So every example is a row in Y, and 1, 1, and the rest zeros. Okay, so C different classes and examples. In the query set, we get to C and X, and we have to predict the Y. What's the class of that query set, that query example? All right. So the Bayesian few-shot classification, there's been a number of papers in the last couple of years on this. Most of them follow this framework where we want to have a distribution over some task-specific parameters, phi. You can think of those as the parameters of a neural network, for example. And we're going to share some model parameters, theta, across the episodes. And so we get a prior over phi. And typically what we want to do is evaluate the marginal likelihood. So what's the probability of Y, the labels, given X and theta? And we get that by integrating out the parameters phi. So we want to, so it's the marginal likelihood, probability of Y given X and phi, given times the prior over phi given theta, d phi. Right? Now this is a difficult integral to solve, and so typically you're going to adopt a variational distribution and optimize the elbow, right? And have some Q of phi, some simpler variational distribution over the parameters, and optimize the elbow. So instead, we're going to approach it with a Gaussian process approach to Bayesian few-shot classification. The nice thing about GPs is that they directly reason over the functions that underlie the classifier. And that allows us to capture the uncertainty well. So again, if we look at the marginal likelihood, imagine we have some functions here. We have psi that's going to parameterize those functions. So you can think of psi, for example, as the logits in a classification network, right? So we have the, so now we have probability of Y given the psi, the logits, times the probability of, we have some prior over these logits that given the data X, d psi. Okay, that's the GP version of the problem. One problem with this is that it requires the inversion of the Gram matrix. So here in this term, we're going to have something that's basically involved like the covariance matrix of all the training points. And the complexity then becomes O of n cubed, where n is the number of training points. That makes GPs difficult traditionally to scale up to large data sets. And so one thing that people do is they approximate the posterior by having a set of inducing points and coming up with a distribution based on that, those inducing points. Now, in Fewshot classification, we're in a nice setup because what happens is that our n, the number of examples, if we're thinking of this episodically, n is the number of examples in the episode. So remember, we said we just have a small number of classes like 5 and just a few examples of each of those, like 5 in the example I showed earlier. So n is 25. So then O of n cubed isn't so bad. So poor scaling with the training set size doesn't really hurt us too much in Fewshot classification. There is a problem, though, in that in GPs, we want to form this marginal likelihood. We want to, ideally, each of these distributions would be Gaussian, so that we can, when we do this, makes this integral tractable, right? Where these are conjugate distributions, so we get the product of Gaussian as a Gaussian when we integrate. But if we want to really do softmax classification across different classes, now we don't have a Gaussian posterior. So I think this is one of the reasons why it hasn't been applied to Fewshot classification. It has recently, GPs have been applied to Fewshot regression recently, though, with some positive results. But now I want to go through and get a little technical and go through some of the derivations to see how we're going to deal with this problem of the non-conjugacy and come up with a way of doing GP classification for Fewshot classification. So to start with, we're going to have a binary classification problem. We're going to change from multiclass to binary. We have examples. Again, we have n examples. And then the labels now are going to be binary. We have n binary labels. In the logits, as I said, the underlying function, psi of x, that's where the Gaussian process forms. It has some mean function m of x and some kernel function. That is, this is what I was talking about, like the covariance matrix of the data forms. And so that's the kernel function of all the Graham matrix. It's all pairs. It takes into account all pairs xi and xj in the episode. Our likelihood is just the standard Bernoulli likelihood. It's going to be given by this product across the examples. That's the binary setup. Now, if for our purposes, we're going to what we want to do is compute a posterior over the logits, all right? Because that's going to be part of our important part of our marginal likelihood. And to do that requires these terms. But the problem is that, as I said, the prior and the likelihood aren't conjugate. So people typically adopt the variational approximation. What we're going to do instead is introduce an auxiliary variable omega. And that's shown here in this graphical model. So we introduce this auxiliary variable omega, and we have the graphical model. We observe x. These are the logits psi. We have some parameters theta. So psi is a function of x and these parameters theta. And then y is a function of the auxiliary variable and psi. So the important thing to note is that we're introducing this variable, but it doesn't really change the model because we're going to marginalize it out, as shown over here. We're going to integrate out our auxiliary variable omega. But by introducing it, we now can make the posterior distribution Gaussian, because what's going to happen is we're going to set probability of psi given x is going to be Gaussian, and this probability of y given psi and our variable omega is also going to be Gaussian. So I'll show you how that works. One particular characterization of that is when omega is a polygamma variable. An important identity that's relevant in polygamma variables is this one over here. So, by taking a look at this equation, if we set a to y and b to 1, and we go back here, we can see that we get this logistic over here, right? So we get something that's e to the psi to the y, and then the denominator is 1 over e, 1 plus e. And then on the right side, we see that logistic variable can be expressed as related to a normal distribution, right? So this is a way of converting the binary logistic to a normal distribution. So that's why we introduced the gamma. And so the nice thing about that is that we get a Gaussian likelihood out of it by conditioning on omega. So that's what's shown in this equation here. And we get a normal distribution that depends on the psi inverse times kappa, where kappa is a function of y and psi is just the original omegas, right? So now our conditional posterior is Gaussian, and we get this nice form. So everything is Gaussian, and it becomes tractable. So we have our Polya gamma distribution that can be conditioned on psi, and we do efficient Gibbs sampling that alternates between updating psi given y and previous updating omega given y and a previous value of psi, and then we update psi given xy and the previous value of omega. Okay, so that's for binaries. Now what we want to do is extend that to multinomials. Now we want to say, okay, this was all for binary variables. Now let's see how we can do. If we want to, start tackling Fewshot classification, where we're going to have multiple classes in an episode. So to do that, we turned to a paper from a few years ago by Scott Linderman and colleague, and what they used was a stick-breaking construction. So what happens in this is that you can think of a multinomial variable, right, over k different values as a product of a bunch of binary variables carefully constructed. Okay, if you multiply them in the right way, you get a multinomial variable. And so the stick-breaking construction is a nice idea. The idea is that you have a stick that describes the probability density, and then you're going to stochastically choose some length less than the whole stick, some length less than 1, and consider the probability of that segment versus the rest. Break that part off, and then do the same thing again. Stochastically choose some portion of the remaining stick, and consider the probability of that versus the rest of the stick. Break that off and continue. So you get a sequence of binary decisions, and if you multiply those probabilities, that gives you a multinomial distribution. Okay, so so that is that stick-breaking construction, and then they showed how, in order to do that, you can use Polya gamma variables. Right. So I like the example that they showed here. So I wanted to give you an example of what you might want to do here. We have dependent multinomials, which is what's the target of this same thing. We have dependent multinomials of, what.
Looks like we lost Rich there. Oh, there he is again.
And so you can see that is this is Scott in New York over the years, and this was like the name Matthew in New York over the years, and this is the name of Scott in Texas over the years, right? So different states have different things, but the idea is that neighboring states will have similar distributions. So this is also shown over here. This is the probability of the name Ethan in different states. So down here is like, in the southeast, Ethan is kind of popular, not so much in the northeast, but a little bit of over here, more in the northwest. All right, so we have this nice spatio-temporal smoothness assumption across years and across states, and the name counts are modeled as multinomial draws. So we adopted this approach and found that there were some issues that were involved in it. So, so one issue is that, well, before I get to the issues, let me just first introduce the notation. So we have our setup, again, for multiclass GP. We have X now is going to be an episode, right, with n different examples, and Y are our labels and different examples of C classes, one hot encoding of that. And we want to lay out our logits. So our logits are the inputs to the softmax, right? The softmax is e to the FIC, for example, I, for probability yi equals some class C. So e to the FIC normalized by the sum over all classes C prime, e to the FIC prime. Right? So the F's are the standard logits, and you can lay them out as one large vector here. And what we're going to do is have a GP over this very large vector. So it turns out that the integral identity for the Polya gamma variables doesn't readily extend to this formulation. So we have to do some other calculations. So one tricky aspect, for example, in this in the stick-breaking construction, is that it's asymmetric. So when you consider the probability of the first segment compared to the rest, and then the second segment compared to what's left, you get to the end of the stick by that time you have very little data because you have to have all of the other things weren't true. So you have very few examples. So it was very hard to get that to work. So we couldn't just kind of out of the box take the stick breaking construction that was proposed earlier and use it in our case. So we were looking for other ways of doing it. And so so to extend to the multi-class, we wanted to choose different kinds of activations that weren't as simple as what was proposed there. So one idea was the error correcting output codes. So that is a way of dealing with multiple classes. And so you assign like a binary code vector for every class, and then you have a separate classifier for each bit in the code vector. So that's one way of doing this. Another method of doing multi-class that still keeps things binary in a way is the robust max. So that one says, take your distribution, take whatever probability is the max of all of them, and then take the remainder of that density and distribute it evenly amongst all the other possible values, the other k-1 values in your multinomial. What we chose instead was something called the one versus each multi-class. And the way the one versus each worked is, or the motivation for that you can see by looking at the original softmax. So this is the softmax here. And if you take a softmax, you can rewrite the denominator in this form as the sum over of an exponential of a bunch of differences of the logits between classes. And that can be bounded by this product over the classes. And that product over the classes is now a product of sigmoids of the difference in the logits, right? So this product of sigmoids over the logits is really what the one versus each is. So that's just to be clear. So the probability of y equals of the class being C, given the logits, is defined to be a product of sigmoids of the difference in the logits of all classes C prime not equal to C. All right. So that's the one versus each construction. So we're going to use that to combine it with the polygamma to get a multi-class GP. Okay. So so this is the description of how that's done. I don't know if I won't go through all of the details of this, but the basic idea is that we have start with our classification logits. So you'll notice that I switched from psi being the logits to f's, and that's a bit of that was necessary just because we wanted to deal with these differences in the f's as being related to the size. Okay, and we have the one versus each likelihood now as the product of the sigmoid of the psi j's, where the psi j's depend on a particular selection of these differences in the f's. Sigmoids of the differences in the f's. And now if we apply polygamma augmentation, in this case, we get the same nice result that we showed earlier in the binary case, where we can get a Gaussian likelihood out. We get the probability of y, the labels given psi and our polygamma variable, as a product of a whole bunch of terms that end up being Gaussian. Right? And then we get conditional expressions that are very similar to the binary case. We get the probability of f as proportional to two terms, right? Or probability of y given f and probability of f given x, right? So again, this was like our likelihood, and this was our prior over f. And now both of these are Gaussian. So when we take the product of these two things, we end up with something that's normal. And so then again, we can do our Gibbs sampling and alternate between sampling the f's and sampling the omegas. So that's our multi-class GP. So this is now, if we want to apply it to Fewshot classification. So the standard setup again is we have a set of labeled examples, our so-called support set. There's n of those labeled examples in an episode. So this whole thing, just to reiterate, this whole thing is like an episodic setup. So we're doing like a GP that's going to be applied for every episode. However, there's going to be some parameters theta that are shared across episodes. Okay, so that's important. So in every episode, we're going to construct a GP that's going to have some examples X and some labels Y in our particular query set. And so what I'm showing over here on the left is similar to the binary case. We have introduced our polygamma variable, and we have something that's related to it's like the logits f in this case that depend on some parameters theta and x. And now y is going to be conditioned on omega and f, and both of those are Gaussian. So when we take the product of those things, we end up with a Gaussian likelihood. And now at test time, what we want to do is introduce some query x and get a posterior over f, and then we'll get a posterior over y star over the labels y star. All right. And theta are these parameters that are learnable parameters in our covariance function. And they could be parameters in a deep neural network and or like traditional kernel hyperparameters. And so what we're going to do is have them be parameters of the neural net as well as kernel hyperparameters. Okay, so that's a nice, I know it's a lot of acronyms, but we have an OVE, PG, GP applied to FSC. All right. Learning in this approach is the traditional kind of learning is marginal likelihood in GP. So the marginal likelihood is just or the log marginal likelihood is this expression integrated over our auxiliary variable omega, probability of y given x and omega. And we do this in practice by optimizing based on some posterior samples of omega and approximate that by this sum over the samples. All right. And we can also optimize in our experiments. We also optimize based on the predictive likelihood. And I'll get back to that in a couple minutes. And finally, we do posterior prediction on the query examples, y star given x star, x and y. Okay, so now we're going to look at some results. So the initial results in this approach is we're going to do look at the standard benchmarks. So these are the standard benchmarks. Cub are the birds. We're doing fine-grained classification on birds. And remember, the Fewshot classification, new classes at test time compared to training. One shot means we only get one example of each of the new classes. 5 shot, we get 5 examples. And you can see some numbers here. So the things we're comparing to, one of these, so baseline plus plus is one of the methods that uses a deeper kind of in a batch pre-training approach. It gets rid of episodic and kind of violates some of those assumptions of episodic and of using a simple network. And they have some of the state-of-the-art results on these benchmarks. But on the Cub, these are the kinds of results that they get. We're also going to compare to prototypical networks and matching networks in mammals, some of the original ones I mentioned in this area. Another one is feature transfer that's fairly recent. GPNet plus linear is worth mentioning here because this is another approach that's an alternative Gaussian process formulation of this problem, where instead of thinking of it as a multi-class classification, it just converts it into a least squares regression. So think of each class as just like a continuous value now, and you want to optimize the least squares difference between the label, which is one of those values, and the prediction. All right, so that's a GPNet plus linear is an approach to that. Think of it Fewshot classification as a kind of regression problem. So our polygamma, does competitively. We do pretty well on 1 shot and pretty well on 5 shot for Cub, and for mini ImageNet we get some pretty good results here. And this is both with our marginal likelihood and our predictive likelihood approach. We also looked at this domain transfer thing we talked about, right, where you train on one domain and test on another. So that's like training on omniglot and testing on a version of MNIST, and we get competitive results, don't win in every case. Similarly, we can train on mini ImageNet and test on the birds. And again, we get competitive results, but don't necessarily win in this domain transfer. But as we said, we want to go beyond those kinds of benchmarks, but this is interesting because it's domain transfer. Another one is to look at uncertainty quantification through calibration. So calibration, one way of looking at thinking about calibration is that the idea is that the accuracy, the probability predicted for the maximum, the kind of most likely class, so think of that probability under the softmax, whatever is the maximum, that probability should match the accuracy of the classifier over the test set, right? So that's a well-calibrated test set. You want a system to be, when it's confident, it should generally be very accurate. When it's less confident, it can make mistakes, all right? So that's given by, so a good job on calibration is given by this diagonal line here where confidence kind of matches accuracy. And so this is on different data sets. The first top one is on the mini ImageNet baseline, and the bottom one is on mini ImageNet transferring, training on mini ImageNet, but testing on Cub. The top row, I don't know if you get this, probably pretty small on your screen. So the top row is our various methods that aren't Bayesian, and the bottom row are Bayesian methods. So this is feature transfer and baseline plus, these methods that aren't episodic and use deep networks. And what you can see is that they're actually poorly calibrated, both on the within domain and the across domain. These are matching networks and prototypical networks, and those are well calibrated. And then the bottom part of this are the Bayesian approaches. So the relation net is a Bayesian approach, and the GPNet plus linear that I was saying, thinks of it as more of a least squares problem. Those aren't well calibrated. And our polygamma, these are two different versions of the polygamma. Those are pretty well calibrated. The same kind of results hold for the domain transfer. Robustness to input noise. So this is another way of testing them. What we really want to do is how robust are these methods if you're going to, add some noise to the input. So different kinds of noise. You can add Gaussian noise, can add impulse noise, or blur the inputs. So the top part of this is accuracy, and the bottom part of the plot shows expected calibration error. You want low values of calibration error, high values of accuracy. And these are three different data sets: Cub, mini ImageNet, and then the transfer of mini ImageNet to Cub. And what you see is that in general, the methods do pretty well on some of these tests. We do well, we being these last two orange ones are our version, our GP version of multiclass. And so we have high accuracy on impulse noise and ImageNet and low values of calibration error. So we do very well. We don't do as well on defocus blur, for example. So here we have high values of accuracy, but pretty high values of calibration error. All right. So that's robustness to input noise. Another thing that's interesting to test is out of episode detection. So here's a question, which is like, we can the assumption is we have these small number of classes, few shots of each. Each query comes from one of those classes. Well, what happens if we get a query that isn't one of those classes at all? What we'd like to be able to do is say it's none of the above. It's not one of the 5 classes we're evaluating in an episode. Instead, it's a none of the above. So that's an out of episode detection problem, which is difficult, right? So people have shown that that's hard for neural nets in general to realize something is out of distribution. So we tested that here in this Fewshot setting and get a set of results. And in general, we do pretty well on this. So AUC is what's the metric here. We want to be high values of AUC. And you can see that in general, our orange guys are pretty high on the AUC, but not winning in everything, but pretty competitive results. Okay, so the conclusion for this part of the talk is I want to say that the GPs address a lot of the challenges faced by Fewshot classification. It gives us this nice principled approach for reasoning about uncertainty, and we can do some adaptation of the test time by optimizing the marginal likelihood with respect to the kernel parameters. And our posterior complexity, so it's a good thing here that GPs are sensitive to, or it's not a bad thing, it doesn't hurt us that they're so sensitive to the number of data points because we only have a few. And we get some competitive classification accuracy and pretty good job on uncertainty quantification. There's a bunch of open issues, right? This is new work. So one of the interesting questions is, so some of our best results are with a linear kernel, right? We explored lots of different kernels, and it turns out that a linear kernel is best. And that maybe isn't a big surprise because you say, well, there's a lot of power in the deep neural network that's being shared across all of these episodes. And that is something that still bears some thought because it turns out that the linear kernel, the formulation is equivalent to Bayesian logistic regression. And it's also interesting to compare ours to a more standard approach to Bayesian neural nets that's based on having a distribution over the network weights, like I introduced earlier. And that typically is done just with using a distribution of the last layer of weights in order to reduce the complexity of that problem. So then it becomes a little bit more of an apples to apples comparison because our GP complexity scales with the number of examples in the episode, which, as we said, tends to be small, rather than the network size. But if you have a GP that's just looking at the last layer the Gaussian prior just on the last layer of weights, then it also isn't too bad with respect to complexity. Anyway, so that comparison I think is interesting. Also, our results, we have results both, as I mentioned, on marginal and predictive likelihood. In general, our predictive likelihood works better. The predictive likelihood, turns out the gradient is biased, but the results are better, and so we're trying to understand why that might be. One thing is that predictive likelihood is more of a conditional setup. It's like you're going to condition on X star and predict Y star in a different way than marginal likelihood does. There's also some indication in the literature that predictive likelihood may be more robust with respect to model misspecification. Right. So anyways, I think that's an interesting question about marginal versus predictive likelihood. Okay, so in the last couple minutes, I'm going to pop up and talk about some general questions of interest. So I already mentioned that, one of the things I think would be really beneficial for Fewshot classification is to move to some new benchmark data sets to test these things like I was mentioning about robustness, out of distribution, and uncertainty. We also want to move towards more natural settings. So this is already something that's going on in the field. So people are looking at unsupervised and semi-supervised settings in this case, which is very natural. Also move towards more incremental and continual learning, right? It's not very natural to only test on novel classes. In the real world, we see novel classes and we also see old classes. So we want to have a combination of those, and that leads naturally to continual learning. Also interesting is recognition in context. And so for that one, I'll show you a little. So we're doing some recent work with some colleagues on recognition in context. And here's an example of that. So we want to think about, we're moving from one environment to another environment, and what the kinds of objects we learn about are very sensitive to that environment, very particular to that environment, right? So we encounter objects sequentially in some context, and the context transitions tend to follow some distribution. We hang out in a room for a while, see some objects, some of which are new, learn about those, move to another room, maybe move to another place, move to another city, whatever the case is, and we're going to see, in different contexts, we're going to see different things. So we're developing an example here where, let's say you're moving around in a house and you're going to see different objects. So you'll see chairs, you'll see windows and doors, and some of these might be new and you want to learn about those. So we have a way of trying to generate examples by focusing attention on particular ones, and then thinking of those as the inputs to Fewshot classification. All right, so the last 2 minutes, I think I have, talk about a deeper understanding of Fewshot classification. So as I said, I think the jury's still out about episodic training. There's some interesting recent work showing that there's advantages of episodic training, and exploring various ways of combining batch training with episodic training. So the question is, the key question is why? What is it about episodic training that could be useful if it is, right? So what is it that you have a small number of classes that makes the problem easier? Or is it just the presence of a few support examples could introduce some variance? What is it that's really useful about episodic training for this task? And the questions, as I mentioned before, what can and should be adapted at test time? There's all kinds of careful things, not just on the output of the network, but changing the activities on the way up in the network that seems to be important. And so that's an interesting question. The other thing is that this is a nice area to explore. Something I've been interested in for a long time is generative modeling, right? It's a natural one. You just have a few examples. So if you can build a really good generative model of your new classes, that should help a lot with building better recognition models. And I think so far that hasn't panned out the way I'd like to, but that's an interesting open question. Another thing is hierarchical Bayesian modeling. So that seems like, again, a natural setting for this setup for Fewshot classification. Aaron Grant and colleagues proposed such a model for this setting. And so the question is, does that, is the nice thing about the hierarchical Bayesian model is that you have one level that shares information across classes. And then as you go down in the hierarchy, then you get things that are more specific to classes. So the question is, what information is being shared amongst the classes and how can you describe that? So a lot of the theoretical work in this area that tries to make predictions and talk about things like sample complexity, that's a key question, the task relatedness. What information is common amongst the different classes? So what's the right way of formulating that is still an open question, right? So what's task relatedness? People are looking at things like, distances between distributions, KL divergences, other divergences. That's really important. So I think that underlies this last question. Can we say, when is Fewshot classification going to be successful and unsuccessful? Like, you go to different data sets, are we going to be able to do a good job on a very different domain? So can we predict success and understand the complexity of that? And then this is also a ripe area for representation learning, something that Pushmeet mentioned in his talk. A very hot area in machine learning these days is disentanglement. Can we not just learn good representations, but learn representations where the different attributes are disentangled? That seems like something that would naturally be important and beneficial for Fewshot classification. That's still a question. Is that going to be helpful if we do disentangled representations for Fewshot classification? And then this leads into the last question I have, which is, can we learn about parts? That goes back to the original work I was talking about that got me interested in this area, right? The probabilistic programming with parts that had these predefined primitives. So we still haven't been able to solve that problem of saying, sure, we can have a deep network that learns all kinds of features, but are we really learning the underlying parts, the composite that can be composed and forming new objects? And so I think that's a good final challenge that I'll finish with. So that's it for now. Thank you.
Thanks, Rich. We're open for questions. There's one from Curly.
Okay.
How do the one versus all and stick breaking constructions compare as a function of the number of classes?
After the one versus all and stick breaking construction. Right. So our one versus all, the complexity of the one versus all is still going to be n squared, right? Because we have to consider, the complexity isn't as good. We can't scale up to as many classes, right? The stick breaking is just going to do it sequentially, go through the n. Our one versus all is going to be all pairs, so the complexity is worse. It's not too important in this setting, again, because we aren't scaling up to that many classes typically. In an episode, you want to tell apart 5 classes, maybe even 20 classes. So n squared is not a deal breaker.
Okay, I had a question since there's no other questions. This disentangle debate in representations. Is there a good way to formalize what disentangle means? I know mathematically what they mean, but like in terms of real life images or whatever.
Yeah, so I think a disentangled representation, I think there's good ways of diagnosing when things are disentangled. So in other words, if you have an attribute that you're trying to disentangle, like, let's say the color in an image, right? And you want to say some portion of the representation represents color and the rest of the representation doesn't represent color. So one way of diagnosing that is to say, well, if you build a classifier that tries to predict color, if it can do a good job on the portion that's supposed to represent color and a really bad job on the part that's not supposed to represent color, it's some indication that there's no information about color in the part that's not supposed to represent it, and a lot of information in the part that is, right? So I think that's more of a diagnosis, not necessarily a mathematical characterization. That can be turned into something more mathematical, but that at least is some way of telling whether the representations are disentangled.
I see. So you would need to have a list of things that you want to be disentangled and have a test for that.
In some sense, yeah. So disentanglement does typically entail, some understanding of what kinds of things you want to be disentangled, right? What are the kind of attributes that you're trying to disentangle? I think that's in general the case that is a problem not just for disentanglement, but it's a problem for other kinds of current research in machine learning, right? So people are working a lot on, like invariant representations, right? So the idea would be, the domain invariance and these kinds of questions. So in all of those, so far, the methods that people have proposed, you have to identify what kind of things you want to be invariant to, right? We haven't been able to say, well, we want to learn what are the important underlying invariances. In almost all the cases in any case that I'm aware of, there's always some identification of, well, we want to be invariant to this, and therefore we can, test whether we're invariant to it. It's very hard to say, what kinds of things have the invariances emerge, and then us agree that those are the right invariances to find. So I think the same thing's true for disentanglement so far. In all the literature, you have to identify what are the things that we want to be disentangled to.
Okay, thanks. Any other questions? Okay, then we thank Rich so much for joining us from Toronto. And we have a few minutes break before
Okay. Thanks
Thanks.
very much. Bye-bye.